Hello and welcome to this Spike Prime presentation. My name's James Dwyer and we'll get started.
Now, Spike Prime is a really nice addition to the LEGO Education product family, which is targeted around years 5 to 8. So from its very inception, it's been designed with LEGO Education's core philosophy in mind, which is that play is essential to learning and building confidence. Now, that philosophy itself is based on Seymour Papin's theory of constructionism, which is the idea that children learn best when they're actively engaged in constructing something that has a personal meaning to them, whether it's a poem, a robot, a sandcastle, or a computer program. And with that, I guess the overriding philosophy guiding the team that developed Spike Prime was all about helping to build all students' confidence in STEAM-based subjects. First thing I'll do is play this little video. Jump in and we'll actually have a look at the hub, the motor, and the sensors. The first thing you'll notice is the shape alone, which that sort of rectangular shape, making it really easy to build with. Also, the motors themselves are rectangular, such that it becomes really quick and easy just to attach motors, and all of a sudden you've got the wheels connected to the base. So it's very easy to build with. You've also got on the sides there, you've got 3 hubs for connecting motors and sensors. You've got the the on-off button there. There's a 5x5 matrix screen at the front. You've got lots of points of contact to build with. There's a little speaker down the side there. The rechargeable battery is charged there. There's a little micro USB. Inside the hub is a sensor as well. It's got a 6-axis gyro sensor that's quite useful. I'll show you that after as well. So this is a section of the software, and I'll come back and we'll cover the software properly, but I just want to show you this first of all so you can understand how the sensors work and connecting them up. I haven't got a hub connected. If I click on that, I have the option to connect it up. I've got this switching it on via Bluetooth, and it should connect up. And if you see it connect up, it should display there. It displays that Bluetooth symbol for a second there. And I've now got the hub connected. So as we'll plug in the distance sensor, okay. And if I go back to that section, so as I said, it doesn't matter which port you plug it into, you can see here that the distance sensor pops up there and I'm getting a live reading. It's showing 200. Now, a better place to view the sensors is if I come back in here, you can see it's telling me, or it's telling us that I've got a distance sensor connected to port B there. You can see the display, the front display of the hub, okay? If I move my hand closer, you can see the number on the distance sensor going down as I move it forward and away. So now you can see as I connect sensors to the hub, I'll unplug it from port B, just pop it into port F, and you can see it automatically gives us a display on the screen telling us what sensor is connected to which ports. And you can get a live feedback from that sensor as I move closer and away. You can see it's going down to sort of 10 centimeters, that sort of thing. And we can use that in our programs to to create intelligent robots, if you like. Okay, other things, we can connect up a motor at this stage. And the motors themselves, so I'll plug that into port A, and the motors themselves have encoders in them. So not only can we drive them forward and back, we can also get feedback about how much the wheels have rotated. So if we move this around, you can see I'm moving in a positive or negative direction, okay? And you can find out how many degrees the wheels have turned. So if you're measuring distances, depending on the size of the wheel, there's lots of different activities you can do like that for traveling a particular distance and using the motors like that. We've got large motors as well. We've got these medium motors. Then in terms of other sensors that we can use, the color sensor, this will give us a reading of what color is in front of it. So if I wave a red in front of it, you can see the number on the screen has changed, or the dot just underneath the sensor has gone to red. If I put a yellow in front of it, it will show yellow, purple. So there's a whole range of different colors that you can put in front of it. And we'll use that in a little exercise in a minute, in a programming exercise to display that. You can also change it from, testing it in or using it in color mode to reflected light. So for those who are familiar with following lines or grayscale, where you'll get a higher reading depending on how bright it is or reflective the surface underneath it is. So you can see there the yellow is showing up as a very bright sort of 80%, and the blue is showing up as a darker sort of 20%. So that's just a reading between 0 and 100 for the light sensor or the color sensor. Okay, and there's a number of different sort of readings. You can get the raw red, green, blue colors out of it as well. Okay, so another sensor that it comes with is similar to the touch sensor that the EV3 shipped with, if you're familiar with that. Only this one can be used as a touch sensor, but it's a force sensor. So it's how much force is applied onto the thing. So at the moment it's showing 0. It looks like it's saying on, but it's 0 newtons. As I start to press down, at the moment it's registering 5 newtons of pressure, and you can increase the force on that and get it up to 10 newtons of pressure. So you can get all the readings in between. So you can potentially link that to the speed of the motors to determine how fast the motors might turn. There's all sorts of creative experiments you can do with that. Now the other one, I was telling you about how the actual hub itself has a 6-axis accelerometer in it, and it can be used to work out. You can see up here on the display, or you should be able to see the yaw, the pitch, and the roll. Okay, so for those who might understand it, if you were flying a plane, the roll is how much the hub is turned to the left or the right. You can see that changing to a positive degree, to a negative degree there. You've also got pitch, which is, I'm using the plane obviously as the example, how much it's climbing, okay, or facing down. And you've got yaw, which is how much it turns to the left or the right. So you've got that sort of feedback, which you can include into your programs and get that feedback. And you might want the robot to behave in a certain way if it's climbing a hill or something, or descending a hill, whatever you can imagine, sort of thing. Okay. Now, if you find that last one with the a little bit complex, you can also simplify it just down to orientation, and this will tell you which way the hub is facing. So if it's facing, if the front is up, or in this case, as I change it, you can see here it's changing to the top is up, or the right side is up, or the left side is up, or the back is up. Okay, and you get all that feedback, and you can do things with that in the program. So it really is quite clever in that regard. Okay, so that's a short little rundown of the actual, the hardware, if you like, the sensors and the motors and the hub. Okay, and we might have a little go at programming it now. Okay, so we'll come back and we'll have a look at an overview of the software. But at this stage, I just want to show you how the programming works, this sort of scratch-based programming that's involved. So here I am. This is an example of a canvas where we would do all our programming, okay? And here are all the blocks on the side, and we can go through and pick out blocks that we want to do things. So the first thing I want to do, we'll pick out there's this block here when it starts. Okay, when the program starts, these stacks of code are activated based on events. And there's lots of different events you can choose, but for the moment, we're going to choose this one, this default one, which is when the program starts. Okay, I want the motor D to take the shortest path to position 0. Now, as I said, there's encoders on these motors, and they can tell where they are. Okay, and you can tell it to take the shortest path to position 0. Now, position 0 will be down here. So if we put it on the left side or the right side, it'll take whichever is the shortest path to get there. So if I just come down here, down to this bottom left section and click, it will start the program for me. Okay, and you can see there, it just moved. So that program is really simple. What I want next is we'll plug in a color sensor. Okay, and we'll plug that into a port, and we're going to get it to do different things depending on what color sensor we wave in front of it. So I'll just move that to the side. So when the program starts, we'll see that happen. Now we want a different event, and we're going to start a different stack of code for that. So it's automatically detected that it's connected to the color sensor up here is connected to port C. So we'll grab that. Okay. Now, if a red is waved in front of it, okay, so you've got all these different hats, and we can start stacks of code there. If a hat we'll display something on the screen. So we'll come here, and we want it to, we'll clear this, and I want it to display R on the screen. Okay, and so there you go. It's going to display R for red. Okay, the next thing we want it to do is we'll play a sound as well. We'll grab this default one, which is the cat meow. Okay, so it should play a sound for us. Okay, and the other thing I want it to do is move this particular motor. So we'll get it to turn in a clockwise direction for, rather than one rotation, we'll get it to change 180 degrees. We can duplicate this code. And suddenly I've got another version of it. This time we're going to make it, if it's the blue block is waved in front of it. And we'll go back and we'll change it from an R to a B. Okay, we'll also change the sound, the bird sound, okay? And this time we'll make it go in an anti-clockwise direction for 90 degrees. So we can tell the difference between the two. So if I now run that program, and you can see here, I've got a whole bunch of slots that I can download programs into, okay? Now there are 20 different slots from 0 to 19 that I can upload programs into. So if I come back here, I've uploaded into slot 2. So I'll just stop that previous program. Now I'll upload it. Okay, you can see as soon as the program started, it activated this particular stack of code, which set it back to 0. If I wave a green in front of it, nothing's happening. But as soon as I wave a blue, I get the bird sound. If I wave a red, and you might be able to see on the screen, it highlights which block of code it's running as well. So you can see, so that's, that's a really simple little example of how you might code this particular, the Spike Prime in that sort of very simple sort of language. Okay, and when you first start the Spike Prime software, this is essentially the home page. This is where it will start. Okay, and there's these 5 tabs across the top, which is how you navigate through the program. First, introducing it to the students, this is where you would start. Okay, and in here is a little tutorial where you can learn about the hub and how to connect it, and it's some of the basic stuff that I've just gone through with you. So in there, it tells you how, connecting the battery up, how to create your first program. So it's all that sort of, it's a very clear set of instructions to get you started and to see what's happening with the hub. So I just took you through the starting with the hub. The second one here is about motors and sensors, and some of the stuff I just took you through, you'd be exploring in that section about controlling the motors, that sort of thing. And then there's a third activity here, which is make it move. And that's the first sort of activity you might do with them. That's a little activity where you more or less get them to hop along, but they're not allowed to use wheels. You've got to get build a robot that will move, but without using the wheels. So it's a fun little activity. And there's a little video I might show you after as well, which is an example of some teachers doing that activity, which is quite fun. Now, then we get into, after the basics, you get into the real sort of the unit plans or the core of the program. Now, it's broken up into 5 different unit plans. When it was initially released, there was these 4, the Invention Squad, Kickstarter Business, Life Hacks, and Competition Ready. And during COVID, they also released training trackers. And the idea is the Lego are going to continuously evolve this platform as well, and they'll be adding in other unit plans as they go along. So if we jump into Invention Squad, in here there's 7 or 8 lessons in each section, and they start off really easy, just to get started. And here's a little cue here. It tells you this particular lesson from go to woe, from getting the kits out of the box and getting started, which should take you about 30 to 45 minutes. One here that we'll have a look at it in a bit more detail is this super cleanup. And you can see I just expanded that. I clicked the more option. And so it tells us here what we need. We need a spike prime set. We need an empty plastic bottle. We need a ball of crumpled paper, and we need an apple or an object of similar equivalent weight. And it tells you what grades the lesson is sort of pitched at, if you like. So we can watch the video here. And this lesson's going to take probably about 30 to 45 minutes. Okay. Obviously, the lessons can go for longer if you extend them. And there's some suggestions on how to extend it. This is stage 1 of 8. Okay. And that's the same video that we just watched a moment ago. And the first step in the 5E strategy is you're trying to engage the students. And wouldn't it be great to organize a cleanup day? It's a big job, so you're going to need some trash grabbers. So that's what we're going to do. We're going to build some trash grabbers and test how well they pick up different types of rubbish. Then we go to the next tutorial, and that's build. Okay. Now, in an ideal scenario, we've got 1 kit between 2, and they've even divided up the building instructions so that the kids can each have a turn at building part of the robot. And then they can come in here and start gathering the litter that they're going to do the testing with. Okay, so that was the empty water bottle, those sort of things. Okay, and here's the instructions, the program that the kids can upload into the grippers to get them working. We're doing a couple of different tests here. First test is about the object size, how well it picks up, each of the grippers pick up different types of objects. And the next one is how well each of the grabbers picks up objects. And then we've got so what's your conclusion? So the kids have to assess the grippers and see which ones were most effective. And also then there's this sort of extension activities where they can then work out whether they can improve on the grippers they've got and build better ones. By no means are the ones provided the best example of what can be produced. They're just examples for the students to test and get them started. So that's an example of one of the units inside Invention Squad. We can come into Kickstarter Business. Okay, there's all sorts in here. Place your order, out of order, track your packages, keep it safe. This one's got a little bit more of an entrepreneurial bent. We've also got life hacks here, got competition ready. So this is about getting ready for different competitions that are out there. Okay, so whether it's the Robocup Junior Australia competition or the first Lego League or other competitions that are out there as well. We've also got training trackers. which is using a lot more the accelerometer inside the hub to track things like steps, those sort of things. Now I want to take you into where the teacher resources, where you might go, some of the online additional resources there. So you come down here and you can get more information online. So if you go there, you just say that you're a teacher, pull it across. Okay, so when we come here, I clicked on the Invention Squad and I'm in Super Cleaner. And if I click into that, you've seen the student side, here's the teacher side. And this is where it comes through and breaks the lesson down for you. So remember when I was referring to the 5E mode of learning or teaching? And we've got this idea that we'll spend 5 minutes trying to get the kids engaged with the topic and make it meaningful for them. We'll spend 20 minutes exploring and building and creating it, 10 minutes explaining where the kids come back, and then there's an elaboration phase, and there's also an evaluation phase as well. In here, there's the sort of key objectives of what we're trying to achieve, okay, what the students will achieve, things you'll need, okay, and then we've got additional resources. If you as a teacher are not quite sure what the solution is, you come into this teacher section and you'll be able to find some solutions there, which is really great. There's also ways you might differentiate the lesson to make it easier for some students or harder for some, or more challenging for some students. Okay, they've also got assessment opportunities, and this is for each unit plan where there's a teacher observed checklist, self-assessment for the students, or peer-based assessment that you might choose to engage with. Okay, there's also language arts extensions here, maths extensions. Now they've gone through and linked it to the Australian curriculum, which is wonderful. And here's examples of some of the standards that you can are achieved through this lesson. One thing I wanted to show you as well, the Robocup Junior run a competition, only for Spike Prime entrants. I'll play it for you. I think it's really quite engaging.
What a beautiful creature. It's crazy to see these in the wild. But you don't want to get too close because they can tend to be a little bit... Crikey! Hi, my name is Naomi. And I'm Jessica. And this is Frizzy, our frilled neck lizard. For this challenge, we wanted to make an iconic Australian creature that people could recognise from the way it looked and moved. That is when our mentor threw in his 2 cents worth. We decided to do a frilled neck lizard because we thought the frill would look amazing. Also, we could add sensors to make the robot react the same way that a real frilled neck lizard would. We think that we have done a fantastic job. We shared the designing and the building, but Jess worked on the programming, and we both worked on the video. The hero element of our robot is its frill. Early on, we worked out that the frill operated similar to an umbrella. Once we worked out how to build the umbrella mechanism, we then had to work out how to get the motors to move them. Our final design uses a rack piece to slide the frill up and down, with gearing to speed up the movement. The frill was too slow at the start, so we tried many different gear combinations to get the fastest possible movement. We added an ultrasonic onto the neck of the lizard to detect objects within 15 centimeters. We coded the robot to react when a hand is placed in front. In videos, we noticed that the lizards would often open their frill and turn their heads back and forth in a threatening way. We mimic this by using a turntable that allows the neck to turn around. The legs go round and round like riding a bike, with the front and back legs going up and down at opposite times. At first we added castles to the front and back, but the robot will sometimes lose balance. To solve this, we added small wheels under the neck to provide extra stability. Frilled neck lizards walk with their heads held high to make themselves look big. To make our robot look like this, we had to make the front legs a bit longer than the back legs and angle the head to point upwards. Finally, the tail was added with slippery pins to make it move as the robot moved. We limited movements of the tail parts near the body so the tail didn't spin out of control and so it looked more realistic. We enjoyed building with the Spike Prime kit, and we really liked the new brick and motors. We found them much easier to add into our build. My favourite part of this challenge was programming. I found programming Scratch much easier to do. My favourite part of this challenge was getting the frill to work and scaring our dog with it. Thanks for watching. I'm Naomi. And I'm Jessica. My name is Naomi. And she's Jessica.
Okay, so you can see there a really cute video, really well done. You can see it's a great example of the kids sort of what they've created. You know, that sort of frill neck or the umbrella sort of mechanism they've created is really quite impressive. And they were the winners of the competition last year. So to go there, you can just type RCJA, which would be Robocup Junior Australia. So if I typed in RCJA there into the Google, it will come up there. That's their website. They've gone through and changed it. And the competition that you just saw is this one down the bottom here. You can either navigate there or come down. And in here, you can see each state is running these competitions. There's a Spike Prime kit is a prize. And here's the 2021 challenge that you can see there. And it just sort of explains the rules, what's expected, the specifications, submission. You can get sent the notifications, obviously, and about the submission. They've even down to, they've got a rubric about how it will be assessed, and you know, a folio for the students to download it and fill in to help guide their work, that sort of thing. And you can see there'll be state-based competitions, which will be announced probably in the next month or so. So you know, another really good competition. There's loads of other competitions there. Some of them are super creative. The on stage is you can see here where they've animated things like teddy bears. On stage is one where they're telling a story. So really amazing stuff going on there and done by the students.
Thank you, everyone, and that concludes the presentation.